Welcome back. We discussed the basic SR latch, then we discussed the first improvement, the level sensitive SR latch, and now we will discuss another modification of the basic SR latch, and this is the one we often use, and we call it a D latch. Right? Now, level sensitive SR latch, it was based on the control input. You had a control input which we later on chose to be a clock signal, but you can never guarantee that the stable values, yeah, the unstable value s is equal to 1, r is equal to 1, it may also appear during the positive edge of the clock. So we come up with a circuit wherein we modify the input in such a way that this condition is actually avoided regardless of what the value of clock is. So I'll draw it here. We'll still have the same core element. It will still be the basic SR latch based on the NOR gates. So this is still my basic unit, direct input and a feedback input. Right? So this still remains this. This will always remain the same. The basic unit based on the feedback that stores your bit, it will always remain the same. So this is my Q bar and Q. Now in the previous case, what I did, I actually introduced two AND gates, one here, one here. Fine. Then we used a common signal C, which we later on connected to a clock signal. Clock signal is nothing but a periodic signal, which has a low pulse, which has a high pulse. Fine. Now in D latch, what we do is we connect one input directly, and then the same input is connected to the other AND gate, but via a NOT gate. Something like this. And this input we call a D input. Fine. So this is what is known as a D latch. Right? So a D latch, if I write it here, so its behavior is that a D latch stores whatever value is present at the D input when clock is equivalent to 1, and later on holds that value when clock changes to 0. Right? Now you can see, since I'm connecting the same input directly and through a NOR gate, the condition 1 1 can never exist. You can see if D is equivalent to 1, this and provided clock is high, I have a high pulse of clock. D is equivalent to 1, so this is 1. Clock is high, so here it will be 1. D is equal to 1, because of this NOR gate, it will make it 0. And if the clock pulse is high, this is 1. So the basic element will have 1 0. Other ways around, if D is equivalent to 0, the NOR gate will make it 1. So this will receive 0, this will receive 1. Again, this is a valid state. This is a stable state as far as the basic SR latch is concerned. Right? And this is the one we frequently use because it is simple and it makes sure that the condition 1 1 it never exists. Right? So we can, as a simple operation, when D is 1 and clock which we apply at the input C is 1, the latch, because that will give the rise to the condition as being 1. Right? So the latch is set to 1, because in that case S will be equivalent to 1, R will be equivalent to 0, and you know that in a basic latch This is basically the set condition. And in a set condition, your latch stores a binary 1. Fine. So similarly, when D is 0 and making sure the clock that applies at the input C is 1, the latch is reset to 0, which means S is equivalent to 0, R is equivalent to 1, and in a basic latch, this is the reset condition. Right? So by using the NOR gate, we have assured that the condition S and R is equal to 1 does not exist at the same time. Fine. And again, this is a simple schematic. We typically show it. Just a second. Like this. We have a D input and a clock, Q output. And as you know, Q bar, which we show just for the sake of completion, something like this. D input, C input, Q bar, Q. So this is my D latch. This is the one we use. This is simple, and it makes sure that the indeterminate state does not appear. Fine. So now we have two modifications, the level sensitive SR latch and a D latch. And we can actually construct a state equation for them. For example, if we consider the first one that we discussed in the last video, the level sensitive SR latch. So in this, let's assume Q at time t, which is the previous state. You can say this is the current state, this is the current input S, current input R, and Q t plus 1, the next state. And so we typically make the tables for sequential synchronous sequence circuit in this way. Right? So current state Q2, let me assume it is 0. It means currently the latch is storing a value of 0. Fine. Then if S is equivalent to 0, R is equivalent to 0, you know that at this condition, whatever was stored, the latch will continue to store that value, the basic SR behavior. So S is equal to 0, R is equal to 0 will make sure your next state is also 0. Right? Similarly, if your current state is 0, but S is equivalent to 0, R is equivalent to 1, so it will enter in the reset state, in which case also your next state will be 0. In this sense, the reset state mein your output is 0. Fine. Then if current state is 0 and set input goes 1, reset goes 0, then your next state will be the set state wherein it stores 1. Fine. Likewise, if current state is 1, S is 0, R is equivalent to 0, you will maintain that state. If current state is 1, S is equivalent to 1, R is equivalent to 0, again set state. And if current state is 1 and set is 0, reset is 1, then in that case, your next state will be reset state, which is 0. Fine. And like I said, in level sensitive SRLI, there is still a possibility that S is equivalent to 1, R is equivalent to 1 may appear at the input when the clock pulse is high. So we'll also list that, although we try to avoid this, but in case it happens. So if your current state is 0, then if S is equivalent to 1, R is equivalent to 1 appears, this still is an indeterminate and it will break down into oscillations. And if current state is 1, S is equivalent to 1, R is equivalent to 1, so this is an indeterminate which you cannot define. Fine. Now based on that, if you remember when we did combination circuit, from the truth table we actually came up with an equation, although here it is used in an entirely different sense, but I can actually use a concept here also. So if I have because now I have three input variables, Q, T, the previous state. If you consider this as the previous state, this becomes your current state, but most of the books consider this as a current state, and this then becomes my next state. Right? So we can actually construct a Karnaugh map here. I'll show you something like this. It will have fine, and I will treat two variables s and r on this side, s complement r complement s complement r sr sr complement, and this q, remember this is the current state. Fine. Now it is one here, here, here. Fine. So this is s. So this particular one is qt bar s r complement. So if you can identify this cell, this basically is this cell. Fine. Similarly, you will have a one here and a one here. But you also have these two indeterminate states, and you can actually treat them as don't care conditions. Fine. Then you can simplify it. This will be your one combination and another one from this side. Fine. So come up with a kind of a Boolean expression, although we don't call it Boolean expression, we call it a state equation. But we are using the concepts of Boolean laws here. So this will be S plus R complement Q of T, and you have to make sure that SR is equal to 0. Yeah, in other words, you make sure SR is never equal to 1. Right? So this one here, this basically is a state equation for a level sensitive SR latch. You can do a similar analysis for a D latch. Let's try here. For a D latch, it is very simple because you only have one input that is being fed directly and via a NOT gate to the basic SR latch. So again, I will have some current state. I have the input D. From these two, I have to actually come up with the next state. Similar way. So if my current state is 0, D is also 0, I'll maintain the next state as 0 based on this behavior here. This a D latch stores whatever value is present at the D input. So it's based on this. And if it is 0 but D is equal to 1, it will change state to 1. If current state is 1, D is 0, will maintain that state. Sorry, it will change to 0. And if current state is 1, D input is 1, then 1. Fine. So whatever is at the D input, as you can see, 0, 0, 1, 1, 0, 0, 1, 1. So it has a very simple equation that Q T plus 1 is actually equivalent to D. Fine. So whatever is at the D input, given that you have the high clock pulse, it will be passed on and it will be stored in the D latch. Right? So D latch has a very simple behavior, and that is the reason it is being used frequently. So these are the state equations for the level sensitive SR latch, and this one is for the D latch. I'll stop here this video.